So what is the first quantization? The first quantization basically means that you are moving from classical mechanics, which describes large-scale objects, to the realm of quantum mechanics, subatomic particles, small scales, etc., the world of atoms and subatomic particles. It means that you are promoting variables like position, x, momentum, p, energy, e, angular momentum, and other variables in classical mechanics. These are quantities, scalars, vectors, whatever, but these are quantities. You are promoting these to operators. So you put this hat saying that this is an operator now. For example, for the momentum in X representation in quantum mechanics, you have this form. It's a derivative with respect to position with some coefficient. I is the complex number, h bar is the reduced Planck's constant, and energy goes like this, time derivative basically. Okay, so you're promoting these variables, classical variables like position and momentum, to operators. And then you add also that these quantities, these operators now, should satisfy some commutation relations. For example, in this case, we insist that position x and momentum p as operators should satisfy this commutation relation. But basically, this is x p minus px. This is the definition of a commutation relation. Okay, this is the first quantization. Now, you might ask in quantum mechanics, what objects these operators operate on? Well, wave functions, right? Wave functions give you the probability amplitude, probability of finding a particle in a given volume in space, or particles if you have n particles, for example. In general, they're acting on vectors in a Hilbert space, which is an inner product space mathematically, but you know that in the wave mechanics, it's easy to think of wave functions. So, for example, momentum and energy operators acting on a wave function psi should give you something like this. Okay, so in this way, it's easy to understand what the Schrödinger's equation, for example, tells us. It tells us something about the energy relation. It says that Hamiltonian total energy of the system acting on psi, the wave function, as an operator, h is an operator now, which is given by this relationship in classical mechanics, should give you the energy operator acting on psi. Energy operator is a time derivative. So from there you get the Schrödinger's equation.